webcam. Let's see how that works. Does that work? Oh, so this is the microphone now. That is weird. So, okay. So, and I guess MATLAB came up. I just wanted to use it to hide the screen for a minute. So the next section seems so weird, but actually it has justification later. But it's a matter of notation. And so let's say there was a person here, A, and then say a person here, B. And I'll go ahead and go through it, and then I'll show you why. Which is what he doesn't. He doesn't do that. So if you drew a vector, you could write RA, and then of course you could write RB. And then you could write a vector that did like this. Now the question is, what generally is this called? And so the whole point of this is there's a certain way to write this vector. And that vector is R to B originating from A. And so there is, there is a reason, but give me a second and we'll get to the reason. So if you write this RA plus R like this is equal to RB. Now, I think the reason he does this is that if you look at the subscripts, I don't know how you spell mnemonic, so there's a nice little mnemonic or accounting thing to keep up with that. If I look at the subscript and just write the subscript down, and just think to myself, well, if I do this, I get that. And so that's one way to remember this. That's not actually, you're not multiplying anything, you're adding, but this is a way to remember that, okay, this cancels that and you get back B. And so that's a way to remember it. It's not, you're not actually doing that, but that kind of makes it kind of convenient. So then the next thing you could do is take a derivative, or I think in the book what he does, I think he first does this. Oops, sorry. And then you can just replace that with velocity of A is equal to velocity A plus velocity B relative to A equals to velocity of B. Now just kind of stop here for a minute and think about this one. And here's the reason we do this. Now he does this, he has several problems, and I'll do one of them in a minute. But the key here is, or the reason why you're doing this, is what if this A and B are connected as a member, like a rod here or something? Then two things can happen. Okay, let's start looking at this funny term here. This term leads to this one, which is that one. So this is, philosophically, this is the velocity that the person at A, okay, so person at A sees, that kind of looks weird, sees the velocity at B, and he sees velocity of B relative to A. So in other words, if this is, in this particular case, if it is a rod like this and it's a rigid rod, the distance between them doesn't change. but all A will ever see of B is it rotating around it. So if you're sitting on an object, you're sitting on this table and it's floating through space, person sits here, person sits there, all they see is each other rotating around each other. So all they see, if it's a rigid body, is velocity of B is only rotation. Then if I had some description, so if I had this and say a description of the speed of rotation, I can get this. So in other words, if A and B were on this member here, and a few seconds later they're here, and it's the same rigid bodies, I'm trying to make it look the same. Then this part moved to here, this part moved to here. But the person who sat here and looked at this, all they would see is it rotating around. That confines things and makes it easier to deal with things.
Why are they rotating?
Well, it doesn't have to be rotating, but if the body is rotating, in other words, what I'm saying is that's all that person will see. They will not see a translation. So now they are translating. This person A is translating, but it's like us. I mean, we sit here and we just see the sun go up and down. And if I sat in this chair long enough, I think I'm still. But in 24 hours, what's the radius of the Earth? I forgot. 8,000 miles?
Something big.
Something big. So you know, just by sitting in that chair, you would have traveled all the way around the world and back. And I don't know what speed that is, but it's moderately fast. So in fact, you think you're still, so the person A might think he's still, and he judges the world around him by seeing things move, but in fact, he's moving. And so what this does, and I'll just go straight to the meat of the issue, is if you, like for example, an automobile, this is a bad drawing of one, but the engine looks kind of like this. So the piston goes back and forth, you know, and this thing is rotating. But actually, a person who sits here and here, if you, I mean, it's hard to think this way, but if you were sitting at A, looking at B, you would see it basically, you would see it kind of go up and down, and up and down. That's all you would see. But you yourself are going up and down, well, you're going around too. So you yourself are going this direction. So actually, since it's pinned here, I can determine the velocity of A, and then I can figure out the rotation that this person at this pin observes of B. But you know B only goes either to the left or to the right. So you have these sort of constraints. You can work your way down to the point where you can find what this thing appears to be rotating with, some omega, which we'll get to that later. And you can actually go, and your goal is to go this one final step. And here's why. You go to acceleration of A plus acceleration of B relative to A equals acceleration of B. Now, you find any particular one of these, okay, let me retract that. You find this one or this one, and then you can find out the forces. Let's just take A, for example. It doesn't matter which one you do. It equals to the mass of the stuff and the acceleration of A. So you can figure out forces on linkages, which that may be important, but it may also be equally important just to find the rotation. For example, let's see. Let's say you had a real short thing like that, and then connected to a rod with a really longer one. that's not as long as I wanted to make it. So let me make it go way out and make it a bunch longer. Okay. So let's say this is a motor and it goes round and around. And so this time, well, let's list this as A, this is B, this is C, and this is D. Well, you know this thing's just going to go round and round and round, but you know this thing can't go around and around because it's too long. This distance from D to C was much longer than A to B, so it's just going to go whoop, and then turn around and go and back and forth like that. And so you can do things like say it's on an assembly line. That looks weird with the C right there. Say it's on an assembly line and it has a funny arm that goes out and does something. I don't know. Maybe it moves a bottle on an assembly line. Maybe it does something. Anyway, you've decided you needed to have something done. And so what you decided you wanted to do is you decided you want to make this linkage and put a little tiny motor back there that just makes this thing go whoop, whoop. And so it goes out, maybe it goes out and grabs something, and and of course in this sequence, the way I've got it, it would be harmonic in the sense that if this is driving at a constant speed, this would be constantly going out and doing that. We can look at mechanisms for film and stuff. You can find that things like this in it. Actually, it's a little bit more complicated and actually more interesting. But the key is, you're going through here, you can find out, the path. I've got the C in the way again. You can find the path of this thing, where it goes in from and to, or to and from, or whatever. And the time it takes and the acceleration, because obviously when it gets down to here, it's going to slow down, stop, turn and go the other direction, stop. So it's probably going to accelerate up to the point about in the middle, turn around and slow down to stop. So you can find these values here. Well, it's convenient to write it this way because actually now, if you're say on B and looking at C, you got two things that happen. One, if you're on B, here, velocity of B, well, let's do, plus velocity of C relative to B, plus equal to velocity of C. So if you go out, you could say, this is just the spinning velocity. It just goes around, it's constant, goes round and round, polar coordinates. Then you can see this, the person sitting on B sees this rod as going whoop, 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 whoop. And you add that motion together with this, and you get the velocity out here. So you can walk yourself down the length this way. Up here. So that's he does not describe at this stage the reason he talks about this, but this is in fact the reason. And what I'm going to do, okay, so we're in chapter 12, and we already started in chapter 12 because that's the way this book is. And then there's 13, 14, 15, and I think it's 16. So what I'm going to do is next I'm going to go to 16 because this is kinematics, which means position, velocity, and acceleration. So is this one, but this is for rigid. I'll make a word here, rigid mechanisms. So this one's for rigid mechanisms, like gears, tires, things like that. This becomes, but what we're doing there is we're finding velocities and accelerations again. Then you go back here, and then you're doing sum of the forces equal mass times acceleration. Then I believe this is energy, and this is impulse. Or, I guess we'll just leave it at that. It's impulses. But you've done all these a little bit already, so this is nothing really new. This one is new, and that's why when I go to it, I'm going to slow down and spend a little extra time. We can sweep through these 3 chapters rather easily. But this is a notation that actually helps us to make our way through it. Now he's got problems that kind of relate to that. Let me find one of them. Since I got the book up, and I think I assigned one of these. So let's just look at. I do not remember the number, but I'm in the problem, so I can just roll down till I find it. I can recognize the picture is what I'm getting at. That can't be it, because... Okay. Oh, that's right. He's broke them differently here. Okay. Wait a minute. Where's my highlight? Okay, I'm in there. This is kind of where, here's the observer, O, A, and B. There's the notation I was talking about. But then he separated the problems apart now. They used to all be together. All he's done is, probably just because it's an online book. So here's I don't know if the aspect ratio looks right there. So two boats leave a pier at the same time. If boat A, it's shown in the picture, it's 40, and boat B is 30. Determine the magnitude of the velocity of A relative to B, and how long after leaving the pier will the boats be 1,500 apart. Does he say they're constant? Okay, two boats leave there at the same time. If velocity, I guess I'm going to assume. Okay, I'm going to have to assume that it's the boats are moving at a constant speed. So 1,500 feet apart. So here, let me make a note of that. Delta R equals 1,500 feet. Okay, so the boats took off. I think the first thing he wanted to know was the velocity of A relative to B or B relative to A. So determine the magnitude of the velocity of A relative to B. So he wants to know the velocity of A relative to B. So if you're B, this is where, here, let me write that bigger. This is the observer. Oh, that's not, how do you say, that's O-B-S-E-R-B-E-R. And they're being, how about being, I could say observe E, but I don't know if that's a word. Being observed. So you want to know the velocity of A if you were sitting on B. So in this case, I could just write it out there. And in my mindset, I basically could say velocity of B and then velocity of A. And the way I do that is I look at the subscripts. Okay, if I have A, this cancels that, then I have that. So I've got it. So all I need to know now is a little bit of subtraction. Oh, well, I've got to also know the velocities themselves. So A is the upper one and B is the lower one. So what I'll do is write the A and B over here. So velocity of A is equal to, okay, so this is velocity of A. So sine of 30I plus cosine of 30J. So there's that one. This one's 45. B would be, and so I'll just, but you know what? I forgot to put the 40 there. So let me back this up a little bit. Okay, that's 40. And now I got to put in my 30. But this time, it's 1 over, it's 45 here and 45 there. So it's 1 over square root of 2. And so now, I can just subtract those two. And so, okay, so let's just think about it from this point. You're 30, he's going faster than you. So if you're sitting here, you're going to see him kind of getting further away from you. So he'll have a higher component, I think, in that direction. I don't know about that direction. So that's something I'll have to figure out. So velocity A, 40 sine of 30, okay, minus 30 over square root of 2. This will be I, and then I'll just go ahead and 40 cosine 30 minus 30 over square root of 2 and a j. So just out of curiosity, for my own curiosity, I'd like to see what that is. So if I type in VA equals to 40 times, which one was A? That's the, okay. Sine degree of 30, and then I'm going to put cosine degree of 30. If I type that all in, that's the velocity vector that is A. If I type that right. I think I did. Velocity of B is just 30 over square root of 2, right? 30 divided by square root of 2. And I forgot to put my bracket. And 30 divided by square root of 2. And I got that. So then I want to take VA minus VB. And I get this, which, oh, that's interesting. So minus 1.21 I plus 13.4 J. So this kind of indicates to me, oh, the picture's gone, okay. So I copied that down, so let me go back to the picture. So that kind of indicates to me that, okay, so this is me sitting at B. From the X coordinate, you know, it's kind of true to life. In other words, this one will always have to look backwards or be a little bit on, he'll be out a little bit past when it's related to that coordinate. When it's related to the J, he outruns him considerably going that way. So then the question is the distance. Since the assumption would be that they started it here at time equals 0, and I don't know how they can do this, but they instantly had a velocity of 40 feet per second. So the amount of force required, the acceleration would be infinite at time equals 0, and the force would be infinite. So that's, I don't know if that makes any sense. In other words, if you say you have no initial velocity and then instantly you have 40 feet per second, that's pretty bizarre. But I'm gonna say that's okay for a moment. That's okay. And if they left at the same point, the boats themselves were the same boat. One boat was sitting on top of each other. Anyway, we'll assume that the acceleration is equal to 0, and we'll say they left the shore, and we'll say how far are they apart. He wanted to know this. So if that's the case, hang on. We'll just write the equation. Plus v naught t plus the acceleration over 2t squared. That's the standard equation for constant acceleration, constant. But if it's constantly 0, you got that. Which means that R, just pick one, A is equal to, and since he's drawn you to be right there, it's just going to be the time, whatever time that is, VA. So I know this doesn't, the part that's bothersome is that at time equals 0, that's true, but the part to me that's bothersome is an instantaneous, unless the boats were about to crash into each other and they came across the same location. Anyway, let's just assume this for a minute. If that's the case, then all you've got to do is take position of B, or plus R A to B equal to R, RA. Now, if you look at it, actually I have that equation backwards. If this is, hang on, I'll put units here. What is the units? Okay, feet per second. And if I want to know a situation where I've got RA to B being equal to, the length of it being equal to 1500, I've got to figure out what time that occurred. So what I'm going to do is I'm going to say, I want to find that vector's length. And so, since this is velocity A to B, then I can simply say this. I'll erase that and I'll say RA to B equals to so many seconds and 1.21 I plus 13.4 J. Now, if t is equal to 0, they're at the same location, which is not possible because the boats would be sitting on top of each other. But let's just go with that. There's one boat, it's in an alternate universe. One was under the other. So it should have been planes at a different elevation. So then a second later, you multiply this times 1, this times 1. 2 seconds later, this times 2, this times 2. And they're just progressing. Well, at a certain point, I want that magnitude of that to be 1500. So the way I'll do it is I'll go in and go back to MATLAB and I'll find the, velocity and the way I've got it, A, and I can't put a divide by symbol, so I'll do that. And then I'll do the norm, or this is the square root of the sum of the squares. And it becomes 13.4825. So what I'm getting at is the magnitude is equal to 13.48. I'll just say 48. So after 1 second, they're this many feet apart. After 2 seconds, of course, they're 2 times that many feet apart, and so on and so forth. So all you really need to do is t times 13.48 equals to 1500, and then divide that out, and I don't know what that is. I know, I'll do this. 1500 divided by 111 seconds, I think. So does that make sense about? So roughly 111 seconds. So that's essentially, I'm trying to think. Let's go just spin around, because all the problems, they're all relating to that. In other words, all you're doing, so there's A and there's B. So I'll just lay it out like this. So if you got velocity A, here, let's do this. All the problems are in this section are somehow associated with this section, which has to do with this equation. So there's going to be an A and there's going to be a B. And so velocity A plus velocity of B relative to A is equal to velocity of B. Now what's interesting is I can write the equation the other way. Now, what's interesting is what this means. If you look at the values, it's pretty much this. Velocity A relative to B is equal to minus velocity of B relative to A. So as a person in B looks at A, he's going to see, let's just say what they're looking at is this. He's going to see this velocity versus this. So if you basically look at it, I'm going to make it up. I'm going to say this person's going 50 miles an hour. Now, yeah, and this person's going 20 miles an hour. So what he sees is he sees himself going 30 miles an hour faster north. And this was seeing the other one. I'm going 30, but the directions are different because of the way you look at it. So he sees himself one way, and basically it's just, that's all there is to it. So essentially, this is all you're doing. There'll be two entities, a A or a B, or a B or C or whatever. And you can write down the equation. Either you're going to have to write down this one or this one. And then start figuring out how to break it into components. In this one, he's got something with a circle. The guy's going in a circle. So he'll probably describe 224. I think that's it. Okay. So at the instant shown, the car has a speed of 20 kilometers an hour, is being increased at a rate of something, 300, and at the same instant B is decelerating while traveling forward. Determine the velocity and acceleration with respect to B. Velocity and acceleration of A with respect to B. So he's telling you use this one, although you can use the other one and just take the minus sign. In all cases, it's going to be the same. That's what you can do. But to me, I would do it like that. And then, so he wanted to know that, and he wanted to know the acceleration of B. And acceleration of A. So in either case, you want to know this, or you want to know that. So you need to find this, and this, and this, and this, in a vectored sense, and subtract them. And so essentially, you're doing this. Equal velocity of A minus velocity of B. The other way you can remember this, I don't try to remember it this way, AB, AB. I don't try to remember it that way, but I try to remember it this way. Say velocity acceleration A minus acceleration B. And so all you're doing here is he says, okay, increasing car A. Now, I'm going to have to shrink it down so I can see which one was car A. Hopefully I don't shrink it down so much I can't read it. Okay. So this is car A. So he says, car A has a speed of 20 kilometers per hour. Why did he do that to me? So it should be meters per second. So I'm gonna change the problem and say it's 20 meters per second. And it's been increasing by what you'll want to do. Okay. All right. Kilometers per hour, and an hour will give you 3,600 seconds, and then a kilometer give you 1,000 meters. So you just divide by 3.6. So that'll be the answer to the velocity. At a rate is increasing, so he has an acceleration that is increasing at a rate of 300 kilometers r squared. But guess what? He has an acceleration going this way, v squared over r. Okay? At the same instant, b is decelerating. Okay, so I'm going to redraw b here. Now the question is b going this way or that way? And I think it was going north. And in the book, the way I sometimes determine that, if you notice, he has a little shadow, a white shadow here, and a white shadow here, maybe implying that's dust off the car. So it's apparently going this way. Okay. So, but it is decelerating. So it is decelerating at 250 kilometers per hour squared, while traveling 100 kilometers per hour. So if you look at the velocities, that's straightforward. You see a 20 and you see that. So what you see is VA, assuming that my coordinate system is going to be like this. Just, I'm going to say VA, which one's A? It's minus 20. And I'll just go ahead and put a J. And then VB, which is the lower one, which is off the page, is going north at 100. And so that one's pretty simple. The thing about the acceleration is, for the acceleration, okay, so that's the velocity. This is the velocity. The acceleration of A has two components. It has a component going down. Did it say it was accelerating? Increasing at a rate. So it has an acceleration going down, which is minus 300, and I'll put a little box for the unit change. And then it has one going back to the left, and that's the v squared over r. And that would be, okay, here. The box means you multiply to change the units. This means you're going j. This means you're going I. So you have the acceleration A, but the acceleration of B is just straight forward. It just goes down 250 times the thing to change units times j. And so this one has two components because you have an acceleration coming in and accelerating. Here's your decelerating, but you're not turning, so you have just a straightforward. And that's all there is to these. So again, it's basically recognize the equation, and the rest of the problem is, okay, can you actually figure out what these two are? And that's it. But the eventual goal is the next chapter, when we get in there, to start doing mechanisms, or lay the foundation so you can start doing more mechanisms and stuff. So all these are, that's all these things are. You notice there's two of everything. This is one where one of the person's, people or whatever, is on the shore. There's the observer from the shore. There's two cars again. There's he's throwing a football and trying to, so that guy can catch it right there. Oh, and that's it. So at this point, what I might do, just spend a few minutes, like 2-3 minutes, to kind of lay out. Okay, so if you look at the thing here, I don't know if I can increase, if I do a control, oh yeah, the words do increase. So if you look, chapter 13 is, okay, so this is called kinematics of a particle. So a particle means an object with a mass that doesn't have a rotation. Then you got force and acceleration, work, and then 15. And so here's the 16 I was talking about. So if we go there, what you'll find is when you're talking about rigid bodies, that's kind of where this is, to me, chapter 16 is where the engineering takes place. Because rigid bodies are what you're going to kind of try to design. So he takes off and goes through here. I'm just going to spin through it real quick. So here you get types of motion. You get pure rectilinear, curvilinear, but still no rotation. Then you can have rotation. Then you have general motion, rotation, and so here's a mechanism or a engine or whatever that is. Oh, and then I got to jump. Okay, so then you got rotation about a fixed axis, absolute motion analysis, relative, and so here's the part where let's make it. So you got an object that is a rigid body. So the distance between A and B are not changing, but it's spinning somehow. And so he goes through the thing, he describes it, he comes up with the equation, and if what you notice here is he says, move that closer. Okay, he says specifically, okay, where did it go? Okay, well, he says specifically, maybe when I spun it together. Oh, here we go. The change is of the motion is just due to translation and rotation. This is due to pure translation. In other words, where are you at A going to? And when you look at B, if you're a fixed distance from A to B, you only see B rotating around you somehow. So suddenly you start seeing, hey, wait a minute, I can use this notation to make things simple. Oh, there's a mistype right there. It's okay, it's translating the book to the internet. It's probably not that easy. So then he gets down in here, he does slipping of wheels and all sorts of stuff like that. Oh, and then I guess I can't just, oh geez, now I'm, okay. So that, we'll just come back and go through. So what we're going to do is go through 16 next. Because 16, and what I'll do is slow down and make sure we get everything out of 16. 12 was only to set us up. 16 is where the engineering happens, but then you really need to know the 13, 14, and 15 as well. But they're not as in-depth, or they are in-depth, but they're not as hard. 16 can be difficult. So try to get the homework done. I mean, if you missed that one on Wednesday, it's okay. I can watch people as they come in, and I'll backdate I can backdate it. When I do, it may take a day for the grades to automatically update. So just go do it. It's a finicky system. I've noticed that some people will complete their problem, look immediately. It didn't change the score. I can actually go change the problem. Go back and look at Blackboard. It didn't change it, but an hour and a half later it did. So I think what it does is their system sends the data over, like maybe every hour or something. I don't know. Maybe it's every 15. I haven't figured it out. Maybe it's a random time. I don't know. Or maybe it's when Blackboard asks for it. I don't have any idea. So